Hi there. So today I want to talk to you about one-way ANOVA. Now this lecture I adapted from a different textbook. It's Utz and Heckard's Mind on Statistics. So if you need to know the reference, here it is. So first of all, let's define ANOVA. ANOVA is an acronym. Of course, we scientists can't get enough of our acronyms. So the acronym stands for Analysis of Variance. So ANOVA is a tool or a test that's used to ask, is the difference between three or more groups statistically significant? Now a one-way ANOVA only tests the variance of one variable. So for example, you might be testing the effectiveness of a diet on people from different populations. And in that case, the variable that you might be measuring, for example, and basing your measurements off of, would be the number of pounds lost while on that diet. We already discussed how to compare two groups. So for a reminder, if you need it, there's that lecture on histograms and distribution functions where we talked about the t-test. So you might ask yourself, well, isn't that good enough, right? I mean, if I have something that can test and tell me whether two measurements are different from one another statistically, wouldn't that be enough? Couldn't I just keep doing that over and over again? Well, that could get pretty tedious if your groups, if you have a large number of groups. So the ANOVA was developed to help figure it out when you have three or more groups. So what does ANOVA do? Well, ANOVA tests whether the means, or the averages, between samples from different populations are statistically significant. Now let's unpack some of that jargon there. Statisticians use this sort of language all the time, but you might not be used to it if you've never had statistics before. So we define a population as something that represents all the constituents that might fall into that category. So for example, all the women born in the United States between 1975 and 1985. But it would be unreasonable to administer a test to every single person in that population. That would just be unreasonable. It would be expensive and super time consuming. So instead, what's commonly done is that you draw from a representative sample of the population. And you might test, say, 100 women that fall into that population. So that's your sample, okay? You're then assuming something. You're assuming that the sample that you've taken accurately represents the population. Now sometimes that's not true. So that's why statisticians are very careful to make the distinction between a sample and a population. In ANOVA, what you're testing is a null hypothesis. So what the null hypothesis is if it's true, then that means that there's no statistically significant difference between the sample means. In other words, all your different groups really have the same average within the uncertainties. If the null hypothesis isn't true, then that means that at least one of the samples has a statistically significant difference from the others. Now, it's not saying that all of them do. It never says that. It just says that at least one is statistically significantly different. So, if you're going to claim a statistically significant difference, the variance between your groups has to be large enough to overcome the natural variation within the group. To visualize this, I've adapted this really nice figure, okay? So here we see three different Gaussian distribution functions. There's a blue, a red, and a green. And you can see that they each have different peaks or averages. But you can also see that there's a certain width to those distribution functions. And so what you're trying to see is whether the width of the functions is too wide to say that the averages really are different, okay? So the variance between the group sample means has to be large enough to overcome the natural variation within the groups. Now, to do this, you're going to need to utilize a new distribution function called an F-distribution and a new statistic called the F-statistic. Okay? So you first have to calculate the F-statistic in order to perform analysis of variance. Conceptually, what the F-statistic is the variation among the sample means divided by the natural variation between the groups. So once F is calculated, we then determine whether that F-statistic should be that big if the null hypothesis is true. And to do that, you compare the value that you got for your F statistic to the F distribution function for your sample, for your groups. So this is a new one for us. I'm not going to ask you to know the F distribution function to the same level that I ask you to understand the Gaussian distribution function. But basically, here's an F distribution function, okay, right here. Now, like all distribution functions, the area under the curve gives us the probability that a value should fall within the integrated range, all right? The F distribution plots the probability density on the vertical axis and the F statistic on the horizontal axis. It always comes to some kind of maximum somewhere near the left, and then it has a long tail as it decays off for larger values of F to the right. In this image, there's a red area shown underneath the curve. Now for this image, that red area is 0.05. Remember, this is a distribution function. So if I integrated it from 0 to infinity, I would get 1, right? Or 100% probability. If my area underneath my curve is 0.05, then that corresponds to a 5% probability or chance, right? Now this 5% threshold is a common threshold for comparison when doing ANOVA. Another common one is 1%, but we're going to dwell on the 5% threshold today. So if you look, you can see that the red area under the curve starts at a value of F, but it's about 3, okay? And so what you're doing is you're integrating F from 3 to infinity, okay? Or you're seeing what the probability is that F would be greater than 3, okay? All right, so if you had an F statistic that was bigger than 3, then that would mean that the probability that it would be there would be smaller than 5%. Now, if your threshold for comparison is 5%, like I said, that's a common one, then that would mean that your null hypothesis has failed, because the chances that the sample means are the same are low. They're less than 5%, okay? So the sample means are not the same with a 95% confidence then, and that means that your null hypothesis failed and your means are different. Now there's certain assumptions that you do when you're doing this test. First is that the samples are independent and the errors are random and not systematic. The distribution of the values in each sample should be Gaussian, okay, or follow the normal distribution function. If you have an extremely skewed distribution, usually the ANOVA is not going to be a good test for you. Also, the standard deviations of the groups can't be very different, not super different. They can be a little different, of course. A guideline or a rule of thumb is that the largest of the sample standard deviations can't be more than twice as big as the smallest sample standard deviation. If that works out, then generally your ANOVA will work. Before we get into the rigors of calculating the F statistic, let's define all of the variables that we're going to be using in this equation. We're going to be calling the number of groups that we have that we're comparing K, okay? Remember that K has to be 3 or greater to do ANOVA. Otherwise, you should just do a t-test. We're going to call the mean of each sample group, however many you have, right? It's going to run from 1 to K. We're going to call that X sub I bar, okay? So that's the mean of sample group I. Now we're also going to be calculating the mean of all the values, and that will just be plain X bar. We're going to be calculating the standard deviation or variance for each group. The standard deviation of sample group I we'll call S sub I. Now, if you've forgotten, remember that the way that you calculate a standard deviation is given by this formula here at the bottom of the slide. So the standard deviation for sample group I would be the square root of 1 over Ni minus 1, where Ni, by the way, is the sample size of sample group I, or the number of constituents in group I. So that's the square root of 1 over Ni minus 1 times the sum over all your groups, right, all your group members, Xi, group member I, minus the average for group I, Xi bar, in squared, right? So that's your standard deviation formula that we covered some time back. The variance is defined as the standard deviation squared. Okay? So if Ni is the sample size of sample group I, we also have big N, which is the total sample size. So that's the total number of measurements that we have. Now you'll note that statisticians might use different symbols. We've been using sigma for our standard deviation symbol. They use that for the standard deviation of the population most of the time. And then they use S for the standard deviation of the group. Okay? All right. Now remember that we said that the F-statistic was defined as the variation among the sample means divided by the natural variation within the groups. So how are we going to calculate those two things? Well, the real formula looks like this. F is equal to MS groups divided by MSE. Now MS groups is a variable name that we've chosen to mean the mean square for the groups. It measures how different the groups are from one another. You sum over the number of groups, K. So here, the mean square for the groups is equal to the sum of N sub I times xi bar minus x bar squared. So remember, N sub I is the number in group I times the average for group I minus the complete average over all values squared. Okay? And then you're going to divide that by k minus 1, where k is the number of groups. And you're going to do that summation on the top from I equals 1 to k. So that's MS groups. Now MSE is in the denominator. That stands for mean square error. It measures how much the groups are expected to vary based on their standard deviations or variances. MSE is equal to the sum times N sub I, the sum of N sub I minus 1 times the variance for group I, or SI squared. And then you're going to divide by big N, the total number of constituents, minus K, the number of groups. That's your mean square error. Okay? Now, these formulas are pretty meaningless until you start to apply them to a specific problem. So the problem that I've chosen to show here is example 16.3 from the Minds on Statistics book that I talked about earlier. That problem goes like this. Suppose that a researcher does a randomized experiment to compare the mean weight loss for 3 different programs for losing weight. And the observed weight loss after 3 months are found as follows in the table here. The weight loss is given in pounds. Okay? So they're trying to get these folks to lose weight, and they're comparing 3 different programs for weight loss. Program number 1 has 4 members. Program number 2 has 3 members. And program number 3 also has 3 members. Okay? So there's 3 groups. And then the N sub I's for each one of the groups are 4, 3, and 3. Now the number of pounds is recorded here. So in program 1, one person lost 7, one person lost 9, one person lost 5, and another person lost 7. Then the program 2 values, 9, 11, and 7, and the program 3 values, 15, 12, and 18. And that's how many pounds each person lost. Okay? So let's identify our variables here in this problem. First of all, we're testing 3 different weight loss programs. So we have 3 different groups. So K is equal to 3. Next, we would have to calculate the mean of each sample group. Okay? So program 1 is group 1. The mean of 7, 7, 5, and 9 is 7. Okay? So X1 bar is 7. The mean of 9, 11, and 7 from program 2 is 9. So X2 bar is 9. The mean of 15, 12, and 18 from group 3 is 15. So X3 bar is 15. X bar would be the mean of all 10 of these numbers. And if you average all 10 together, then the mean of the total sample, X bar, is equal to 10. SI squared is the variance for sample group I, or the standard deviation for each one of these groups squared. S1 squared is 2.67 pounds. S2 squared is 4, and S3 squared is 9. So those are the variances for each one of those groups. n sub I is the sample size of each group. N1 is 4, N2 is 3, and N3 is 3. The total sample size, big N, is 10 because there were 10 people participating. So now we can go through and we can see how we would plug into these formulae. So for example, MS groups here, that's the sum over n sub I times xi bar minus x bar, quantity squared, divided by k minus 1. So to plug in for that, looking at group 1, it has 4 constituents, and 1 is 4. And then it would be 7 minus 10 squared. The 7 comes from the mean for group 1, and the 10 comes from the average for all the groups, and then you square it. Now you sum up the same idea for the other two groups. For program 2, it's got 3 constituents. The average for group 2 is 9, and then you're subtracting off 10, the average for all the groups, and you're squaring it. And then for program 3, yet again there's 3 participants. The mean is 15, and you're subtracting off 10, and you're squaring it. And then you take that whole sum, and you divide it by k minus 1. Since k is 3, k minus 1 is 2. And that would be how you would calculate the variable MS groups, which goes into the numerator of your F-statistic. For more details on how to calculate this, I've expanded it all out again here for you. As you can see, when you calculate MS groups, you get 57. So 57 is the value for MS groups. Now we need to calculate the denominator in the F-statistic. That's MSE. MSE is the sum of Ni minus 1 times the variance, and then divided by N minus K. So plugging into that, there's 4 minus 1, or 3, for that first part, and then the standard deviation squared of the variance for group 1 is 2.67. For group 2, it's 3 minus 1, or 2, times the standard deviation squared, which is 4. And then for group 3, 3 minus 1 again is 2, times the variance 9. So that's your numerator. And now you're dividing by N minus K. Remember, big N is the total number of participants for all these weight loss programs, which is 10, minus the number of groups, which is 3. And 10 minus 3 is 7. So when you divide the numerator with the denominator here for MSE, you get a value of 4.86. Right? Now we can calculate our F-statistic. The F-statistic is MS groups divided by MSE, which is 57 divided by 4.86. And when you do that division, you get an F-statistic of 11.74. Okay? So we've gone through how to calculate an F-statistic. But now that we have it, what do we do with it? Okay, well, we need to look at the F distribution and then figure out where our F-statistic of 11.74 falls on our particular distribution. Now, the thing about the F distribution is where the peak is of the distribution and how long the tail is, those depend upon your situation. Okay? The location of the maximum and the length of the tail are actually controlled by 2 variables. These variables are generally referred to as the numerator degrees of freedom and the denominator degrees of freedom. In the plot above, what they've done is they've shown you, how many is that? 4 different F distributions for different degrees of freedom. And they show here in the legend the numerator degrees of freedom, comma, the denominator degrees of freedom. You can see that as the number of degrees of freedom gets smaller, the F distribution shifts more and more to the left with its maximum. And you can see that as the degrees of freedom gets larger, the distribution function actually starts to look more and more Gaussian in nature. Okay, so how do you find those 2 variables, the degrees of freedom for the numerator and the denominator? Well, the numerator degree of freedom will be equal to the number of groups minus 1, or k minus 1. And the denominator degree of freedom will be equal to the total number of constituents in all of your samples, big N, minus the number of groups, k. Okay? So for our example, we had 3 groups. So the numerator degrees of freedom is 2. We also had 10 total participants for those 3 groups. So N minus k, or the denominator degrees of freedom, is going to be 7. or 10 minus 3. So if you plot what the F distribution is for numerator degrees of freedom 2 and denominator degrees of freedom 7, then it looks like this. It almost just looks like a decaying exponential, all right? So that means that we had a very small number of degrees of freedom, and our peak got shifted so far to the left that it looks like that decaying exponential right there. And the tail is really long, okay? Now our F value is 11.74. Remember, the F distribution plots on the vertical axis the probability density, and on the horizontal axis the value of F. So if I show you where our value of F is, that's indicated by the blue arrow here, and it's pretty far to the right. So what that means is that the probability of having an F value that large is going to be pretty small. You can see that the probability density is a really small number out there, where F is 11.74. That means that having that F value that high isn't very likely, and so we could already probably guess that we're going to reject that null hypothesis, which would mean that at least one of those three programs gives you a different result, and the means don't overlap. Okay, but we need to be better than that. We need to do better than probably and maybe. We want to establish confidence limits on it, right? So how do we do that? Well, you can do it a couple of ways. You can use Excel, for example. That's maybe one of the simplest things that comes installed on all computers without having to pay a lot of money, right? At least the ones here on campus. So we can use Excel to return the probability that the F statistic is 11.74 or higher. This is our probability value, or our p-value, to speak statistics with you. Now to do that in Excel, you can enter this command. In a cell, you type equals F-dist, F-D-I-S-T, and then parentheses, and then you put your F statistic, in our case that was 11.74, and then a comma, and your numerator degrees of freedom, and then a comma, and your denominator degrees of freedom, right? And then you close parentheses. So here we had equaled F-dist 11.74, comma 2, comma 7, because that was our numerator and denominator degrees of freedom. And our F statistic was 11.74. When I did that in Excel, I got a p-value reported from Excel of 0.0058. What that means, what Excel did, is it integrated that F distribution function starting at 11.74 and going to F equals infinity. And when it did that, it got 0.0058. What that means in everyday language is that you would get only a 0.58% chance of having an F statistic that's that large or larger, okay? If the null hypothesis were true. Since that probability is less than either a 1% or a 5% threshold, then we can reject the null hypothesis because the chances of that happening are very low compared to our threshold. That means the three groups are different. So see, now we've quantified it, and we've said that there's a greater than 99% confidence that those three groups have at least one member that's different. Now, that's one way you can do it. Another way, if you don't feel like using a computer program, for example, is to use some tables that have been compiled. See, this is something that gets done often enough that just like the Gaussian distribution function with the t-value tables, okay, there's tabulated whole tables full of these values. So let me get you used to looking at some of these tables. This is yet again a table that I borrowed from Mind on Statistics, but similar tables exist all over the web and in most statistics books. Okay? So what you've got along the top of these tables, right, is the numerator degrees of freedom. So in this particular table, you could go from a numerator degree of freedom of 1 all the way up to 10. And then in the vertical here on the left-hand side, you can read off the denominator degrees of freedom. Here, I just cut off the table so that the font would be big enough to maybe read on the slide. It goes from a denominator degree of freedom of 1 to 10 here. Okay? Now, you find out what the F threshold value would be for your particular F distribution. Remember that we had a numerator degree of freedom of 2, which is right here, right, in that second column there. and a denominator degree of freedom of 7. And then you triangulate and find what your F-statistic is in the table. And the F-statistic is 4.74, and I've drawn a little red circle around it so you can see. Now, this table from Mind on Statistics reports the value of the F-statistic at the critical or comparison value. Now you can see here, there's a little cartoon in the upper left, and it shows you alpha equals 0.05. So this is the threshold value of F, and if you integrated from that critical value of F to infinity, you would get 0.05. So if you had an F-statistic for 7 numerator denominator degrees of freedom of 4.74, then that would mean that you would have a 5% chance of having that F value or higher. Well, our value was 11.74, and 11.74 is greater than the value of the table, which means that your percent chance is even less than 5%. So if you're going to reject at the 5% level at an F statistic of 4.74, then you sure as heck would reject an F value of 11.74, right? Because 11 is greater than 5, okay? So that means that if your F statistic is greater than the threshold value, that you can reject that null hypothesis, that at least one of the groups has a mean that's different. So that's how you use the tables if you want to know whether or not to reject your null hypothesis. Okay, so I think it's fair at this point to sum up. Remember, if you're doing one of these problems, one of the first things that you might be asked to do is to identify and calculate all your variables if they're not provided. You need to find the number of groups K, the total number of data points N, the means for each group, xi bar, the group standard deviations or variances, SI squared if it's the variance, SI if it's the standard deviation, the overall mean x bar, the number of numerator degrees of freedom, K minus 1, and the denominator degrees of freedom, N minus K. Once you've identified all those variables and written them down, you might need to then plug those variables into a formula and calculate your F statistic if the problem doesn't provide it. Once you have your F statistic, then you've got a couple of choices. You can either use Excel or another program and find the p-value for your F. And then you're going to calculate or compare this p-value to your threshold value, usually 5% or 0.05 or 1% or 0.01. If your p-value is less than 0.05, for example, if that's your threshold, then you can reject that null hypothesis because the chances that your F statistic would be that large are smaller than 5%, or whatever your threshold is. You can also, if you don't have access to a program like Excel, use tables to find the value of the threshold value for your F statistic for your desired level, usually 5%. And then, if your F statistic is larger than the threshold F statistic, you can reject your null hypothesis because that means the means are significantly different. Okay, that's how to perform a one-way ANOVA. I hope you enjoyed it. Remember, you can always rewind, pause, all that kind of stuff, and I'll see you in class.